Good day, class of 2022. Welcome to today's Physical Sciences lesson brought to you by the Gauteng Department of Education in conjunction with Saibono Discovery Center. My name is Bongani Mabuya and I will be with you throughout this lesson. Today, the topic of the day is electric field. That is what we are going to talk about. We are going to talk about electric field. So it is continuation from what we have done yesterday. And again, you'll be assessed based on electric field, more especially under electrostatics. So let us look at the lesson objectives. What is it that at the end of the lesson you should know? Today we are going to define electric field. That's number one. Number two, we are going to define electric field at a point. And then we are going to draw electric field patterns, then perform calculations. So this is the order of the day. We are going to provide electric field at the point, define electric field, draw electric field patterns, and calculate electric field. Let's look at the concept map. I did say that we have to associate charges with electrostatics. So we are still continuing with the issue of charges. So when we talk about electric field, it has to do with charges. So the concept map, it illustrates the origin of charges, conservation of charge, non-contact forces, which is electrostatic force, and electric fields. So this is what we are going to talk about today, electric field. So we want to understand what is this electric field. Furthermore, it is going to link to when charges experience repulsion and when charges experiences what? Attraction. So our best weapon is the exam guideline. I did say that there is nothing that we can do besides consulting the exam guideline. So it is important to make sure that the exam guideline becomes our friend. So let's look at the exam guideline. What does it say about electric field? So it tells you describe electric field as, because this is how we define electric based on what the exam guideline stipulates. So we cannot come with our own alternative definition from the textbooks. We need to define all the terms the way they appear from the exam guideline. So this is what we are preaching. Have the exam guideline with you. It should be your friend. You need to consult the exam guideline. So the exam guideline, it is telling you define electric field as. So this is the content of the day and we are done. So define electric field as the region of space in which electric charge experiences what? A force. So this is what an electric field is. It is a region of space in which electric charges experiences what? A force. So that is what an electric field is. And you need to emphasize this definition to yourself by repeating it, sing it to yourself. So definitions, they should be our national anthem. Sing them. The best way in ensuring that you comprehend and you can recall a definition, it's when you sing it to yourself. So sing these definitions according to the exam guideline. Let's provide definitions the way they appear from the exam guideline. So it tells you define electric field as a region of space in which electric charges experiences what? A force. So this is powerful. This is powerful. So we have covered the first point. We did say that today we are dealing with simple things. We are defining electric field. We are defining electric field at a point. We are drawing electric field patterns. And we perform what? Calculations. So let's provide definitions. And this one, you tend to take it light. It is being assessed in grade 12 as well. So do not only focus on electric field at a point. You look at the exam for the mere fact that this concept is included in the exam guideline. It means it is eligible for assessment. So define electric field as a region of space in which electrical charges experiences what? A force. Here is an important thing. It says that the direction of the electric field, this is very important. The direction of the electric field at a point is the direction that a positive test charge would move if placed at that point. So when you draw your vector diagram, you consider the positive test charge. It is the movement of the positive test charge placed at that point. So we are here to deal with that misconception as well, to say that let us be sober when we deal with electric field. So we have defined electric field as the region of space in which charges experiences what? A force. And we are saying that the direction of the electric field, it is that of a positive test charge when it moves placed at that point. So the exam guideline is then telling us that expect to draw electric field lines. Sometimes they call them electric field patterns. So the exam guideline is telling you that expect this. You will be required to draw either a single point charge or 2-point charges, where one is negative and the other one is positive, or where one is positive, the other one is positive, or where one is negative and the other one is negative. So you need to expect that you will be required to draw the electric field pattern, or you'll be required to draw electric field lines of a charged sphere. Let's move on. The exam guideline then stipulates that restrict to situations in which charges are identical in magnitudes. Then it continues to say define electric field at a point. So there are two definitions that you need to make sure that you can recall them. They must be embedded to your mind. Electric field and electric field at a point. So define electric field at a point as the way it appears from the exam guideline. So it tells you that electric field at a point is the electrostatic force experienced per positive charge placed at that point. So that is electric field at a point. So you should be in a position to compare and contrast electric field and electric field at a point. And this is a common question that is asked, electric field at a point. So when we talk about electric field at a point, we are talking about electrostatic force experienced per positive unit charge placed at that point. So you need to sing this definition to yourself. Sing it to yourself. So this is what we are saying, that we are going to take definitions the way they appear from the exam guideline. So when we talk about electric field at a point, we are referring to that test charge, a positive test charge. And we are saying that it is the electrostatic force experienced per positive unit charge placed at that point. Placed at that point. So that is what electric field at a point is. It is that electrostatic force experienced per unit positive charge placed at that point. And it tells us that you are going to use this equation to calculate for the electric field at that point. Because we are talking about E, which is electric field, F, electrostatic force, and Q, we are talking about the charge. And it can be quantization charge as well. So it is not only limited to quantization of charge. It can be also a charged sphere. So this is the equation that is acceptable for you to use. And as well, it tells you that solve problem using this equation. So what does this mean? It means that you can be assessed to calculate for electric field at a point. You can be assessed to calculate for electrostatic force, provided that you are given the value of electric field. And also you can be required to calculate for a charged sphere. So the question is saying that you will be required to solve problems using this equation. And let's look at the units for electric field. The units for electric field is newtons per coulomb. We'll come back to that. Then it says, calculate electric field at a point. This is what it says. The exam guideline is telling us that you will be required to calculate electric field at a point using this famous equation. E is equals to kq divided by distance squared. And the distance squared is between a positive test charge and a charge. So it is very important to familiarize yourself with the exam guideline, because it does provide an indication what is it that you'll be assessed on this content. So let us be sure when it comes to definitions, because it's 2 marks or nothing. Electric field, it's a region of space in which electric charges experiences a force. When we talk about electric field at a point, we are talking about electrostatic force experienced per positive unit charge placed at that point. Placed at that point. Okay? So it does say that restricts to 3 charges. So we cannot go beyond 3 charges when we perform these calculations. Let's move on. Now let's talk about the electric field pattern. You will be assessed about this. And this is where we need to grasp marks. We cannot afford to get a question like this incorrect. So this one, when you get a question that requires you to draw an electric field pattern of a charged sphere, you need to be happy that you are being awarded marks. So those marks, they are yours to consume. So eat them. Eat them. So let's talk about electric field patterns. There are certain guidelines that we need to follow when we draw electric field lines of charged spheres or points. And the first one, it says electric field lines, they must start from the surface of the charged object. So this is where the line should start from the surface of the charged object. Number 2, electric field lines, they do not touch each other. So electric field lines, they cannot cross each other. So when we have more electric field lines, more especially if they are closer to each other, it means that your electric field is stronger, it's denser. And if you have electric field lines that are apart from each other and fewer, it means that your electric field strength is weaker, it's less dense here. And we are saying that electric field lines, they must have direction. So these are arrows that start from the charged sphere. So this is the guideline of drawing an electric field line on a charged sphere. So it is important to remember that your lines, they start from the surface of the charged sphere. Number 2, they do not cross each other. They should not touch each other. And these lines, they must have directions. Because if your arrows do not have directions, it means you have written a wrong thing. So it must have directions. Let's move on. So let's start with the first one, a positive charge. So a positive charge, how do we see a positive, or what is the best way of remembering electric field lines of a positive charge? It is that the electric field lines, they go out. So positive out, negative in. So the electric field lines, they go out. That is why you can see the arrows, they point out. Once they point out, you must know that is a positive charge. So you can see that these lines, they start from the surface of the sphere, and these arrows, they have what? Direction. And these arrows, they do not touch each other. So this is what we are emphasizing, that when you draw your electric field lines, make sure that you follow those guidance. Now, when we talk about a positive charge, we are saying the electric field lines, they move out. So once the electric field lines, they move out, then that charged sphere is positive. So positive is equal to out. Now let's talk about negative. Negative charge in. So negative charge in. The electric field lines, they are moving inward. And you can see with the arrow that the electric field lines, they are moving in. So just create a mnemonic for yourself. Positive out. People who are positive about life, you can see that they are obnoxious, they are positive, they are popping. Okay? So positive out, negative in. So we need to associate that. Positive out, negative in. The electric field lines, they are moving inward for a negative charge. Let's move on. Let's move on. Let's move on. And then let's talk about repulsion. Now you are having two charged spheres and they are both positive. You draw your spheres and you draw electric field line. But one thing about like charges, we all know that like charges, what do? They repel. Like charges, they repel. So you still stick to the guidance to say that positive out. All the electric field lines, they must move out. So they must show that these lines, they are emitting out. So positive out, negative in. And if you are going to have an interaction of positive and positive, we are going to have what? Repulsion. But the electric field lines, all of them, they will move out. The same thing can be applicable with the negative. Let's try to draw maybe a negative and the negative. We are still going to experience what? Repulsion. And what are we saying about a negative charge? Is that the electric field lines, they are going in. So you must have the direction that in, 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 in. So that's what we are saying, is that they are going in, 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 they are going in. And the experience is what? Repulsion. Because like charges, they repel. Unlike charges, they attract. So this one is in. Let's move on. And then let's talk about a scenario where we are having what? Attraction. Attraction occurs when unlike charges interact. And we are saying that unlike charges, what do? They attract each other. Like charges, what do? They repel each other. So, unlike charges, here we're having a positive charge. You can see the electric field lines, they are moving out. Here we are having a negative charge. We can see that the electric field lines, they are moving in. But because we're having an interaction of positive and negative, unlike charges, what do? They attract. So this is how you demonstrate the attraction. Is that at some point they join together. And when they join, please take note of the direction. Positive out, negative in. Positive out, negative in. So here we are demonstrating the issue of attraction between charges. So I'm saying that you can be awarded 3 marks for drawing this. Make sure that you draw the correct electric field lines for that certain scenario. Now, let us look at this. Questions. We are told that a small point charge carries a charge of 4 times 10 to the power negative 10 coulomb. So this is a charge. Here at X, this is where we're having a positive charge, or what you call a positive unit charge. This is the test charge. And our test charge is always positive. And that is why we define electric field at a point as the electrostatic force experienced per positive unit charge. So our test charge is positive. Okay? And the exam guideline, it does tell you use the correct signs. It is the positive charge that is going to emit charges or electric field lines, which are what? Which are positive. And when they go and interact with this positive charge, what's going to happen? They'll experience what? Repulsion. Because positive and positive, what do? They repel. And let's look at our distance. The distance is between the charge and a positive test charge. And it is in millimeters. Yesterday, I emphasized the issue of distance. The distance should be in meters. So that is the first stress that you should have. It is to assess whether your distance is in meters or not. So in this scenario, it is in millimeters, meaning that the owner, it is with us. To do what? To convert 30 millimeter to meters. So here are the fundamental questions. Calculate the magnitude of the electric field strength at a distance of 30 millimeters from the point charge. A second point charge of minus 8 times 10 to the power negative 10 coulomb is placed at position X. Calculate the magnitude of the force between charges. And then we have the other one that says identify whether this is a force of attraction or repulsion. So I'm going to do this with you. So already we do comprehend the scenario. Let's respond to the first question. Calculate the magnitude of the electric field strength. And we only have the charge and the distance. So it informs the type of equation that we are going to use, which is this one. E is equals to KQ divided by R squared. So the equation is KQ divided by R squared. You get 1 mark for this equation, provided that you substitute. So I always say that the power of physics paper 1, for you to pass well physics paper 1, write the correct for copy the formula from the data sheet. And then substitute. If you can fight to write the correct formula and substitute correctly, you have won the question. So, for writing the correct formula, provided that you substitute, you get 1 mark. And then what do? You substitute. So what is our K? Our K is constant. It's 9 times 10 to the power 9. And what is our charge? It's 4 times 10 to the power negative 10. We are told. Divided by the distance between charge and the positive unit charge placed at that point. And we know that that distance is 30 millimeters. So you convert 30 millimeters to meters. And I think you will divide by 1000. And then you're going to get 30 times 10 to the power negative 3. Don't forget to do what? To square, because your distance is in squared. It's distance squared. So you get a mark for this. And then your final answer, you get your mark, provided that the units, they are also correct. Newtons per coulomb. So this is how you respond to a question. Let's move on. Number 2, You were told that a second point charge of minus 8 times 10 to the power negative 10 coulomb is placed at position X. So now we substitute position X with the second point charge. Calculate the magnitude of the force between charges. Remember, you had to determine your electric field, which is 4,000 newtons per coulomb. So that's what you have. You have the value of electric field, and now you have the value of the new charge. The question wants the force. So it means then you are going to use this equation that says electric field is equals to force divided by charge. So what is your electric field? It's 4,000 equals to, what is your force? Unknown. Divided by the new charge. You don't put the negative, don't insert the sign. Just put the value of that charge, which is 8 times 10 to the power minus 10. And then what do? You solve for F. So you transpose divided by charge, it becomes times charge. Then you get your answer, which is 3 marks. So 1 mark for the formula, 1 mark for substitution, 1 mark for the final answer. So the question then asks you, for this scenario, identify whether this is a force of attraction or repulsion. So you are having a negative charge that interacts with a positive charge. So you need to recall what you have done even from grade 10. That like charges, what do? They repel. Unlike charges, what do? They attract. So positive and negative, what do? They attract. So your answer will be attraction force. So this is how you respond to a question. So now, here is a scenario, and I am going to give you 2 minutes to copy this question, and then I am going to show you questions.
Excellence. Excellence is a habit. Excellence is a quality you have, a quality I have. It's a quality we have when we honor what is true to us. Yes, we are gifted differently. uNkulunkulu akasinganga ngokufana. Excellence is striving for your best. Whenever you have a particular project, test, homework, uzibuze, ask yourself, is this my best? Can I put in more effort? Excellence is striving to be in the top 1% of the area in which you are gifted. And so I challenge you, in every single thing that you do, in every single area that you're gifted in, whether it's sports, it's academic, ucula, whatever that gift is, strive for excellence.
You have been given power to decide whether you want good results in your life, in your schoolwork, or you want bad results. As Tony Robbins said, it is in the moment of your decision that your destiny is shaped. And your destiny is shaped right now with the decisions that you are currently making in your schoolwork. So decide whether you want to be an A student and start working on it, because there is power inside of you. The infinite power is inside of you, and the time you decide to tap in that power, you will become who you want to become in your schoolwork.
Okay, so I am going to give you, let me see, 2 plus 3 plus 5. So I'm going to give you 10 minutes to respond to these questions. 10 minutes. Good. Now let us respond to these fundamental questions. The first thing, before even attempting to answer these questions, you need to understand the statement. What is it that you are required to do? So you are having two charges here, which is charge 1 and charge 2. Charge 1 is minus 14. This, I did indicate yesterday that it stands for times 10 to the power negative 6. So we need to familiarize ourselves with these two symbols. So the n is times 10 to the power negative 9, nano. So charge 1 is minus 14 times 10 to the power negative 6 coulomb. Charge 2 is plus 20 times 10 to the power negative 6 coulomb. And our test charge is P. And how do we define electric field at a point? We are saying that electrostatic force experienced per positive. So our test charge becomes positive all the time. Just remember that the test charge is positive. And the distance from charge 1 to P, and you need to know the distance from charge 2 to P. Okay. So you are told that 2-point charges Q1 and Q2 with a distance of 3 meters apart are shown below, and charge on Q1 is minus 14 times 10 to the power negative 6, and charge Q2 is plus 20 times 10 to the power negative 6 coulomb. So let's look at the questions. Define the electric field at a point. That is what the question requires you to do. Define electric field at a point. And we did say that we define electric field at a point as the electrostatic force experienced per positive unit charge placed at that point. So this is what electric field at a point is. It is the electrostatic force experienced per positive unit charge placed at that point. Where does this definition stem from? It comes from the exam guideline. So let's write definitions the way they appear from the exam guideline, which is 2 marks or nothing. So when it comes to definitions, it's 2 marks or nothing. So we cannot afford to lose these 2 marks. So let's make sure that we sing definitions the way they appear from the exam guideline. Let's go to the second question. Draw the electric field pattern due to these 2 charges. So we are focusing on 2 charges, charge 1 and charge 2. And let's look at their charge. Charge 1 is negative. Charge 2 is positive. And what are we saying? It is that unlike charges, what do? They attract each other. So you are demonstrating attraction. So you must draw electric field lines that shows attraction between negative and a positive charge. So you can have a negative charge, you can have a positive charge. We are saying that what do? They attract each other. Now, we are saying that positive out. So the electric field lines, they must be emitted. Positive out, negative in. And the electric field lines for attraction, they move from positive to negative. positive to negative, positive to negative, positive to negative. So here you have demonstrated that indeed, unlike charges, what do? They attract each other. So for having the correct arrows, for drawing the diagram correct, you will be awarded 3 marks. Make sure that the electric field lines, they do not touch each other. So this is what the question wanted you to do. So you can see that you have 2 marks plus 3 marks, you have 5. So it means you are winning. What more do you want in life? What more do you want? Let's move on. The third question says, calculate the net. This is what I want. The net electric field. This is what the question wants. Net means total. And if all the charges, they are collinear, they're in a straight line, then what do? We add them together. So this is what I've been saying even on our last lesson, that when charges are collinear, what do? We add them together. So the question requires us to calculate for the net electric field at point P, situated 2 meters apart from charge 2. So the first thing that you do here, you need to draw the vector diagram. That is what you need to do. You need to draw the vector diagram. Good. So here is our test charge. When the test charge interacts with charge 2 on this side, charge 2 is positive. So it means it is going to experience what? Repulsion. So it is going to experience repulsion this side. So this can be E of charge 2. And then when the electric field line from the test charge interacts with Q1, which is negative this side, on your left hand side, it is going to be attracted. So you can see that our E1 and E2, they are moving in the same direction. So then you determine the direction. Let left be positive. I love this. So you say let left be positive. And then what do? Calculate E1 separate, calculate E2 separate. And then what do you do after? You sum them together. So let's start with E1. So we are calculating for the electric field from charge 1. And we can see that it is equals to minus 14. So for charge 1, that's why I'm saying that we draw it like this. When this positive charge interacts with the negative charge, it becomes attracted that way, E1. When the positive charge interacts with the positive charge, it is repelled in opposite direction. So this is what I was trying to illustrate to you. Then you are going to write the equation KQ divided by R squared. That is our formula. KQ divided by distance squared. For writing the correct formula, just copy the formula from the data sheet. It's 1 mark. Then what do? Substitute. What is our K? It's constant, 9 times 10 to the power 9. What is our charge 1? It's 14 times 10 to the power negative 6. So we don't put the sign. Divided by the distance between charge 1 and the test charge. So from charge 1 till the test charge, we want this distance. And we know that the distance from charge 1 to charge 2 is 3 meters. From charge 2 to P is 2 meters. So it's going to be 3, which is 2 plus unknown. So we transpose this. 3 minus 2 is equals to R. Therefore, R is going to be 1 meter. So it's going to be 1 meter. Don't forget to do what? To square it. Then let's perform this calculation. You go to your calculator, 9 times 10 to the power 9, multiplied by 14 times 10 to the power negative 6, all divided by 1 squared. And your answer will be 126,000 newtons per coulomb left. Okay? Then let's calculate for E2. You do the same thing. Calculate it separate. Is equals to KQ divided by distance squared. And what is your K? It's 9 times 10 to the power 9. What is charge 2? It's 20 times 10 to the power negative 6 divided by the distance between charge 2 and P, which is what? 2 meters. Don't forget to do what? To square it. Then you perform your calculation. You can use your calculator there. 9 times 10 to the power 9 multiplied by 2 to the power 9 multiplied by 20 times 10 to the power of negative 6 divided by 2. Don't forget to square your answer. And you're going to get 45,000 newtons per coulomb. So the vector diagram is indicating that everything is going to the left. And we said let left be positive. So you're going to say E net is equal to the sum of E1 and E2. What is your E1? 126,000 to the left, which is positive, plus of the formula, plus 45,000 to the left, which is also positive. Then you punch your calculator. I think you're going to get 171,000 newtons per coulomb left. So this is what the question required you to do. 5 marks. 1 mark for the formula. 1 mark for substituting this side correctly. 1 mark for substituting this side correctly. This is what I'm preaching. That write the correct formula. Substitute correctly. And you can see that already you have 3 out of 5. That is enough. Then 4, 5. Let's move on. Let's move on. Let's move on. So now you can respond to this question, DBE November 2016, question 7. I am going to give you 10 minutes to respond to it. Now, let us respond to these questions. 7.2, a charged sphere A carries a charge of negative 0.75 times 10 to the power negative. I think now we do understand that this sign stands for times 10 to the power negative 6 coulomb. So the first question says, draw a diagram showing the electric field lines surrounding sphere A, 2 marks. So we cannot afford to lose these 2 marks. You look at the charge, it's negative. The charge is negative. So you are going to draw your sphere and say it is negative. And then you draw your electric field lines. Make sure at least that they are 8, 9, 10 so that it looks neat. And negative, we're saying that negative in, positive out. So negative, the electric field lines, they are moving inward. So indicate the direction and make sure that they do not touch each other. Lines start from the surface or the circumference of the sphere. So you get 2 marks for drawing this. So you can see that these are marks that we cannot afford to do what? To lose. And then it says sphere A, the very same sphere A, is placed 12 centimeter away from another charged sphere. Here is that charged sphere, plus 0.8 times 10 to the power negative 6 coulomb. Along a straight line in a vacuum as shown below. Sphere B, it carries a charge of plus 8 times 10 to the power negative 6 coulomb. Point P is located 9 centimeters to the right of sphere A. So we're having a scenario here. Okay, so we know P, it is at that point where electrostatic force is experienced by a positive unit charge. So the first thing that you do when you deal with this problem is to draw your vector diagram. So you indicate your vector diagram. When P moves to sphere A, you can see when P moves to sphere A, it's positive and negative. It's going to be attracted in that way. So you can say that is E of A. We must determine the electric field of sphere A. When P interacts with charge B, P is positive, charge B is positive. It's going to experience what? Repulsion. So both are going to the left. So it's safe for us to say let left be positive. And then once you have your direction with you, then you calculate them separate. Calculate them separate. So you can first determine electric field of sphere A and write down the equation is equals to KQ divided by R squared. Writing the correct formula awards you 1 mark, provided that what do? You substitute. So our K is constant, 9 times 10 to the power 9. And then QA, I think it was minus 0.75. So you can confirm that. It's minus 0.75. That is sphere A. So you don't put the negative. 0.75 times 10 to the power negative 6 divided by the distance between sphere A and the test charge. So let's look at the distance between the sphere A and the test charge. It is what? 9 centimeter. So you need to convert 9 centimeter to meters. And I think you're going to divide 9 by 100. You're going to get 0.09. So it's going to be 0.09. Don't forget to do what? To square your distance. And then let's punch our calculator. 9 times 10 to the power 9. 0.75 times 10 to the power negative 6. All divided by 0.09 squared. And what's going to be your answer? It's going to be 833,333,33 newtons per coulomb. Right? So this is your electric field for sphere A. Now let's look at the electric field for sphere B. You write the equation, copy it down, is equals to KQ divided by R squared. And what is your K? It's constant, 9 times 10 to the power 9. What is sphere B? I think it was 0.8. So it's 0.8 times 10 to the power negative 6, all divided by the distance between sphere B and test charge. That is what the question wants. So let's look at that distance. So we want the distance from B to the test charge. So we need to minus 12 centimeter minus 9. So you're going to say 12 centimeter minus 9, I think it's 3. And it's 3 what? Centimeter. So we must convert this 3 centimeter to meters. And we divide by 100. So I think it's going to be 0.03. Don't forget to do what? To square your answer. Then you're going to say 9 times 10 to the power 9, 0.8 times 10 to the power negative 6, all divided by 0.03 squared. And I think your answer will be 8 million, if I'm not mistaken. Newtons per coulomb. And then what do you do after? That's when you sum these two electric fields. E net, the total, is equals to E1 plus E2. What is your E1? 833,333,33 plus E2, it's 8 million. And what will be your answer? And your answer will be 88,33333,33 newtons per coulomb. Where? In which direction? To the left. So this is what the question required you to do for 5 marks. So 1 mark of the formula, 1 mark for the correct substitution this side, 1 mark for the correct substitution this side. So write the correct formula. This is what we are preaching. Substitute correctly, you'll get maximum marks. And then 1 mark for this sum and 1 mark for the final answer. So this is what we are saying, that when it comes to this question, you need to be comfortable to know that this is where you are going to grasp marks. This is where you are going to get good marks. So you need to be confident. So as I summarize, indeed, it is very important to be friends with the exam guideline. The exam guideline, it tells us everything that we need to know about the content that we have covered. So when we talk about electric field at a point, we define it as the electrostatic force experienced per positive unit charge placed at that point. Placed at that point. So let's see definitions the way they appear from the exam guideline. And these are the acceptable equations that will be required to use to solve problems. So this is what we are saying, that when it comes to electric field, let us be comfortable that we'll get all the marks. Let's fight to win. And COVID is still with us. Let us continue to sanitize. Let us continue to wear our mask properly. Let's maintain social distance. See you next time when we deal with Ohm's law, electric circuits. I thank you. I thank you. I thank you.